Good afternoon, everyone. I hope you are doing all right and welcome back from the spring break. So let's start class by polling on this one first. Oh, seems like I haven't started my clicker thingy. So let me do that. Okay, now I am opening the poll and you have a minute. 30 more seconds. 5 more seconds. 5, 4, 3, 2, 1, and it starts. Okay, let's see what we got. So A and C is dominating. So correct answer in this case is C. So we talked about converging lens, and when object is very close to the, within the focus, what happens? It generates, or it creates, I should say, magnified and upright image. That's what we learned. Okay, and basically that's the principle that this magnifying glass uses. So magnifying glass is just a converging lens, and if we make shorter focal length, magnifying, the magnification becomes even larger. So let's take a look at the ray diagram here to make things even more clear. Okay. So magnifying glass basically makes the image larger, of course, as the name suggests. Oh, my pen is not working. I don't like that. Looks like I have to restart my. Okay, so we have this magnifying glass that magnifies the object, and this magnifying glass has thicker in the middle and it is thinner in the outside, and that's what I am trying to show you. So this kind of lens is called convex lens, and or converging lens, convex or converging lens. And when we put object, let's say within the focal point, what happens? It makes a magnified image, and that is shown by drawing two rays here. One that goes parallel to the axis here is the lens, and after that it passes through the focal point. Okay, another one that goes from the center, it goes undeviated, and these two don't meet on this side So that means they don't make real image in this case. Remember, they make real image if the object is outside the focal point. But once it is at focal point or inside, what happens? It becomes virtual because these rays cannot meet on this side. So when we look through the lens using our eyes, we can see image inside. It looks like it's inside the lens. But if we were to back produce these two rays, what happens? They meet at a large distance, and that's where the tip of the image is. And the image is on the same, you know, orientation as the object is. When we have that kind of situation, we call that upright image, right? And since the size of the image is larger than size of the object, what happens? We say, okay, the image is magnified. And how much is magnified? You know, how much this is magnified can be, calculated by finding the magnification. So since the image is virtual here and we don't know where it is, okay, we cannot measure the image distance. So we cannot use this formula for magnification, negative image distance over object distance. We cannot use that. Rather, we have to use, like angles we can measure. So here we are saying, okay, what angle the image is making in our eye when we are using this lens. Okay, larger the angle, larger the object appears, right? So here this theta is that angle. Added means when we are using lens. Okay, so again, we don't know this, where it is, what's its height, and so on. At this moment, we cannot measure that. So rather than, trying to find the angle using that, what we can do is we can just use this angle because the angle going to be same by made by the object and image, because this angle and that angle, they are both made by the line passing through the lines that pass through the bottom of this object or the bottom of the image and tip of the object and tip of the image. So these two angles are same. So the angle made by rays of light, or let's say image, I should say, the angle made by image in our eye when we're looking through that lens or magnifying glass is equal to angle obtained by the object. So this is the case when we are using lens. Now, to find the magnification, we need to compare that with what's the angle when there is no lens. So that is the situation we're looking at. And we know like near point is the point where, nearest point our eyes can clearly see an object. So what do we do to find that angle? We put object at that near point, and often this near point is denoted by uppercase N. We'll talk a bit more about that a little later. And then now the angle made by that object when it is at near point is the angle without any kind of addition on added I, or just simply theta. So we can write the magnification, also called angular magnification, because we are using angles to calculate that. So theta added divided by theta unadded. So in this case, this simply theta here is unadded. When I was trying to write that unadded as a subscript here, it wasn't fitting on this my image, so I just wrote theta over here. So that's what the formula is, okay? So in this case, what is theta added and what is theta unadded? So we can write approximately those values. So for example, usually what happens is these angles are small angles, so we can approximate them. So this theta, when angle is small, theta is very close to sine theta, and that is very close to tangent theta. All these number becomes very close in radians, okay? So if I think this as a right triangle here, what happens? This is object height, right? And this is object distance, which is P. So ratio of this height and this object distance is like a opposite divided by adjacent. And opposite divided by adjacent is given by tangent theta, which is very close to theta. So because of that, I can write equation something like this. And I can repeat that process for this right triangle. So in this case, same idea. Theta is very close to h divided by this length, and this length is denoted by uppercase N. That's often, that's the notation. So that means we can divide this fraction by this fraction. When we do that, division, we can invert the division and make multiplication. And that's what I'm doing. It was h over n. Now I'm making n over h. So when I do that, the h and h cancels, giving us n over p. Okay. So for a normal eye, remember 20/20 vision, they call it. So in physics, we use that number as a 25 centimeter. Okay. So often this 25 centimeter is considered as a near point for a normal eye. So if there is defect in the eye, that changes. We're going to talk about that very soon. Okay. So we have n over p as the angular magnification. Okay. So it tells us how many times this thing is magnified, and it depends on n, which is fixed for a normal eye, divided by p, and p has to be within the focal point. So that means if the focal point of the lens is, or focal length of the lens is smaller, means this p gonna be smaller. So that means the angular magnification becomes larger. So that's why we need lens with shorter focal length. So that means it has to be thicker, very thick in the middle. Okay. So if you ever have touched that magnifying glass, in the middle is very thick, and then it gets thinner outside. Okay. So that's the reason. And sometimes what happens is we may not know exactly where the object is. If we don't know, in that case, we can replace that by the focal length. They're not always going to be same, but if we are putting this very close to this focal point, that means object distance is going to be very close to focal length. So we can write this equation like this. So this is the magnification. And so for example, let's say if we have our near point for normal eye is 25 centimeter, which I just noticed I had written there. And let's say we took a lens that has a focal length of 5. Oh, it's usually not even 5 centimeter. It could be, let's say, 2 centimeter. Okay. So in that case, I can use this formula to find approximate value of the magnification. So 25 centimeter divided by f. I'm saying, okay, let's say it is just 2 centimeter. So that gives you 12.5 times magnification. Okay, magnification is a number. Okay, so that's how the magnifying glass works. Now, here is a question, and you have a minute and 30 seconds to answer this question. Thirty more seconds. And 5 more seconds. 5, 4, 3, 2, 1, and it stops. Okay, so let's see what we got. The lens equation applies for both real and virtual. That's a B. So many of you have chosen this. So which is not, the question was not, but for both real and virtual image, we can use that formula for the lens, okay, for any lens or even mirror, okay. Only difference is that the sign of the F, P, and Q may be different depending on whether we are using that for converging or diverging lens or mirror, right? So this statement is not a not true statement, it's a true statement. I guess you just try to figure out the true statement here. The object must be placed within the focal length of the lens. So yes, if we want uh, magnified, then that's what has to be done. Okay. So magnification is always greater than 1 when using the lens. It says a lens. It did not specifically said as a magnifying lens. So this usually for magnifying glass, it's more than 1. That's true. So let's see if that is better or this one. A virtual image formed by a magnifying glass can be seen with the naked eye without additional equipment. Yes, we can see that. So that's how we can see it. So as long as we are looking through the lens, we can see it. Okay. But we cannot cast the image on a screen. Okay, we cannot look at the image on the screen somewhere. So looks like that is also correct. So only the statement that may not be correct sometimes is this one. So that's why this is the best. So what happens if we don't set up that lens as a magnifying glass? In that case, what happens? This may produce magnification less than 1. So this is the only best choice. If there was better choice, that would have been the correct answer, but looks like in this case, this is the best choice among these. That's the, only has a little bit doubt compared to other statement. So I'll go with C in this case. Okay. So anything you like to add or ask here? And chat is also open. Okay, then let's move on. So there is this problem. So a biologist, like many of you, is examining a rare insect using a magnifying glass. The lens has a focal length of 12 centimeter. So focal length, focal length is 12 centimeter. We denote focal length by lowercase f, and it is 12 centimeter. And magnifying glass is used, magnifying glass uses the converging lens, also called convex lens. So it has a positive focal length. So I can use that. So that one we have to have in our head. Okay. So it uses positive, uh, you know, it uses convex lens. The insect is placed at an unknown distance from the lens. So that means Q is unknown. P is unknown. And the biologist observes a virtual image that appears 12 centimeter behind the lens. So that means Q is 12, not 12, but 24 centimeter. And it is behind the lens. And it is virtual. If it is forming the image behind the lens, it's going to be virtual, even if the problem did not tell us. So that tells us we need to put negative sign over there. And now it says determine the distance between the insect and lens. So in part A, it is asking us to find object distance. Distance of object from the lens is object distance. So for that, we can use that lens equation we saw in the last question. Like no matter whether real or virtual, you can use that formula, right? So how do I write it? I can write something like this, 1 over Q, 1 over F. I'm solving for P. So that means 1 over P is 1 over F minus 1 over Q. So you can plug in numbers right here, or you can go one more step, maybe even two. So these, I can say, okay, common denominator is F and Q, F times Q, and it's going to be Q minus F. So P going to be opposite of that. So we have used this lens formula for the previous chapters. Hopefully you are comfortable using it by now. Now in this case, it's time to plug in numbers. So F is positive 12, and then Q is negative, so negative 24. And then now Q is negative 24. And then there is negative sign in the formula. And then there is this F. Oh, F is 12, right? So negative 12. So both being negative, they get added. And this negative, when we multiply these two, we get a negative sign in front. We can pull that negative sign in front. And when we do this, let's say how much is the sum? That is negative 36. Okay, so it cancels, giving us a positive number. So insect better be real insect, right? So that's what the positive number means here. And 12 times 3 is 36. 3 times 8 is 24. So I'm getting 8 times, but you folks want to verify numbers using calculator or your head. Okay, so that's how. Oh, sorry, this is not 8 times. This is object distance I am calculating. So its unit must be centimeter. See here, it has a centimeter, it has a centimeter. So centimeter is square on the top, and 36 is the centimeter. So basically giving us just the 8 centimeter. Let's write positive to emphasize the meaning of it. Okay. So you can see this is within the focal length, and that makes sense, okay, for operation of magnifying glass. So focal point is 12 centimeter away, and the object is sitting at just 8 centimeters, so it is within the focal point. So that is part A. Now for part B, what is the angular magnification? So we can use that formula directly, n over p. We just calculated p, so we can use that. And n is 25 centimeter, p is 8 centimeter. So that gives us 3.1 something like that times, right? Okay, so that's how we can do the magnifying glass. So I did magnifying glass in detail because when we are using microscope, for example, designing microscope, what happens? It also has two lenses. One lens is there and the other lenses are here, and you can choose the different focal length to get the larger or smaller magnification depending on what kind of object you are looking at over here, right? So it has both converging lenses, and this one is called objective. These lenses, one of those are objective lenses because it's pointing to the object. An object is close to that lens often, right? So here is that object, and then there is another lens over there, and there is a prism that basically makes the light go through the total internal reflection, so that for convenient like viewing, rather than stretching your head all the way up there, you can watch from there. And there going to be a prism here, there is a prism there. That's what this does. It does not magnify image or anything like that. It simply changes the direction of light. That's it. Okay, so basically these are the two lenses that are working as a compound microscope. So if we were to draw or trace ray diagram, see, this is, we put just outside the focal point so that we get a real inverted image, and this is going to be slightly magnified. Okay, so this is image, real image for this lens. Now what happens is this image acts like an object for this second lens or the eyepiece. Okay, so when that happens, we call that virtual object. See, there is no insect over there, right? Rather, there is already an image of the insect. So this, since this image is acting like object, we call that virtual object for this one, this lens. Okay. So, and now this, we use this as a magnifying glass. We put this image slightly inside the focal point of this eyepiece. So that's what you are adjusting when you are doing it. And then what happens? A very large magnified image is formed, final image is formed, you know, far away. And this image is inverted image. Okay. This image is, see over here compared to this one there. This is the original object. Since the image is forming behind somewhere there, it is inverted image and virtual inverted image, but highly magnified image, you see. So we learn how to find angular magnification of one of the lenses. So to find the total magnification, what do you do is you find the magnification due to one, magnification due to another one, and multiply them. And just like we did before, by using the angles here versus angles over there, and using the similar formula, we can derive the equation of magnification in terms of basically this separation distance, also called the tube length of the microscope. Okay, so here I did not write that, but that's how the magnification works. Okay, in a compound microscope. And there is another device, telescope, that also uses two, let's say we can use two convex lenses just like the compound microscope. So what's the difference between microscope and telescope? Microscope object is very close to this objective lens, but telescope we use to look at the distance object. Okay, so because of that, what happens is the object is very far, so parallel rays of light arriving means they all converge near the focal point. And now you have to adjust this eyepiece just like you did here to get virtual image at infinity. So I did not draw this image. I found this image and I'm using it. It is not that big. Hopefully you can see it. So in this case, magnification for the telescope can be written as focal length of the objective lens, this one. Often it has a longer focal length, divided by this one, which is just like magnifying glass eyepiece. Okay, so magnifying glass and eyepiece, they have shorter focal length, but in this case the objective has longer. So we can write this magnification like this, and these equations are derived just like we did for the magnifying glass, but in this case you have to look for two lenses. And by the way, telescopes, that you can find in the retail stores, that the kids have them. Those kind of telescope, they both uses these converging lens or convex lens, but we can have telescope with one converging lens, another diverging lens, or often the mirrors. They use mirror, okay, large mirror, because telescope we want really large magnification, and for that, or want to see large object from the very large distance. So the light coming from very large distance arriving to the lens going to be very faint. So bigger the size of the mirror or lens we use is going to capture more light, so that the image does not appear kind of like a bit darker. We want bright image. Okay, so because of that, the size of these things are large, and if we make a really large lens, what happens? It gets distorted by its own weight, difficult to, heavy weight, difficult to transport. So because of that, they use a mirror, one mirror, large mirror, and even they make pieces of the mirror and put them together as a big mirror for a lens. Okay, I mean, so sorry, big mirror for the telescope. So that's how these big telescopes that are in, for example, Hawaii. I don't know if you have heard about Keck Observatory in Hawaii, one of the island, right? So that's how they are made. Okay, so that is about the compound microscope and telescope. I just inserted that, right? So here is a question regarding the compound microscope. So I am giving you 2 minutes, maybe a bit longer read here. Thirty more seconds. Five more seconds. Five, four, three, two, one, and it stops. Let's see what we got. So mostly B. And objective lens creates a real inverted image. Yeah, basically that's what we saw, and right? So real image near the focal plane here, this, and this one magnifies. So yes, B is correct answer here. So some of you chose this. So the virtual image, it does not create virtual image. It creates real image, but that real image acts like a virtual object for the second lens or the eyepiece. So I guess that may be a little confusion there. So now let's talk about our eyes. And our eye, they act like a camera, and even better. So here our eye as an optical instrument, because that's what the optical instrument do, right? So they use light and make image of an object. And our eye does the same thing. So here is a little bit fancy sketch. I borrowed the image from, I think, book. And here is my simplified drawing. Okay, not bad. So we have this combo. We can refer those as a lens. Okay, relatively thick lens, and retina is right there, behind the eyeball. And there are these nerves that takes the signal, or they sense the image and tells the brain, okay, that's what you are seeing. Okay, and in my sketch, there is this retina I'm making right here. Okay, so that it's easier to make the ray diagrams. Okay, so how does the eye work? Distance of lens and the retina where the image is formed image has to be formed to be visible, that distance is fixed. Image distance is fixed. So for lens and camera, usually what happens is focal length of the lens is fixed. And for some camera, yeah, point and shoot cameras, the lenses don't move much, like our phone, right? So what happens? Distance between the sensor and the lens is fixed. So just like that, our eye also have fixed detector called retina and the lens. So the distance is fixed, just like our cell phone uh, camera. But these days, the cell phone has different lenses, more than one lenses. So each of those lenses have different focal length. Okay, their size may be slightly different, and the focal length is different. Size means how big the opening is. So that is given by f value, not focal length value. Okay, in camera it's written as 1.2, something like that. So basically that says how big the opening of the lens is. Okay, but a simplest form of camera going to have one lens, and there's going to be a sensor at a fixed distance. So our eye looking at the structure, it looks just like that. But there is one big difference. Our lens, eye lens, can change the focal length. It can stretch, make itself thinner, focal length becomes longer, and it may just, squeeze itself to a thicker inside, a lot more thicker inside, so focal length becomes smaller. So that way, single lens acts like several lenses in a camera, for example, right? So it can change focal length really nice as long as it is working normally. Still, it tries best, okay, but sometimes we need help. We'll talk about that. That's a defective vision. So there are these muscles that basically helps the lens to stretch and compress, so making the lens focal length bigger and smaller. So that's the magic. So although Q is fixed, what happens? Focal length can change depending on where the object is. So for different object distance, the eye changes the focal length and makes image always at the retina as long as it is properly working. Okay. So for example, let's say if object is very far, it says infinity we use. So infinity could be like like 50 or 100 meters could be thought as infinity in this case. Okay. So infinity is not always like, okay, far, far in the galaxy. So it has, depending on what context we are looking at, uh, the infinity sometimes could be in centimeters. When we talk about atomic and nuclear physics later, towards the end of this semester, we'll learn that for the atoms, what happens? Millimeter can be a infinity, can be thought as infinity. Okay. So anyway, it depends on context. For our eyes, distance object, as long as these rays of light are arriving fairly straight, we call that object is at infinite distance, whether it is a moon, sun, or a star, or distance tree, or distance car, or anything like that. Okay. So you need to keep that in mind, okay? So infinity is large distance, and that large is relative, depending on situation. So when it says distant object, for example, in our case, in the note or in the question, that means we can say, okay, the object distance is infinity. So what theoretically it means is that as long as light arrives to parallel to our eye lens, and that means it is at infinite distance. Okay. Okay, so that is infinity, and that's that. And then now what happens? Although the rays of light are coming that far, what happens? It changes now focal length equal to the value of q, right? So that's why it is exactly focusing. So retina acts like a focal point in this case because these rays of light are coming from infinity. And we know when rays of light comes from infinity or parallel to the axis, optical axis, right? So in that case, what happens? It brings those light to the focus. It converges those light to the focus. So that's what we have learned, right? So that means in this case, the value of Q going to be equal to the focal length of this lens or the whatever focal length the eye lens has at that moment when you are looking at that object. Okay. So this is normal eye. That's what it's supposed to do. No matter where the object is, it should form image right at the retina. That way we can see clear image. Now, if it is not working, then properly working, then what happens? Then these parallel rays of light, see, it cannot make this lens thin enough, right? It's still thick, so that's why it's converging before it reaches to the retina. So in this case now, what happens is that the focal length of this lens is smaller than the value of q, means it cannot stretch enough. So it cannot make itself thinner enough to focus at the retina. So it focuses before the retina. So that's why now since the image is not at the retina, means we have blurry vision. And depending on how far it is, we may not even, you know, like see it. Like it's going to be totally like, very blurry. Okay. So this defect is called nearsightedness, also called myopia. So nearsightedness. Sightedness means you can see it when object is near, but you cannot see when object is far. So there are several kind of defects, but here we're going to be just talking about two kinds of defect. Okay, nearsightedness, or also called short-sightedness. Short-sightedness or the nearsightedness. So what happens in this case? The when object is far, it cannot focus the rays, parallel rays of light coming from that distance object to the retina. Okay, it focuses ahead of retina before it reaches to the retina. So that means the lens must have gotten thicker. Your eyeball has now become bit, yes, I don't know, uh, maybe gets elongated and the retina goes farther behind and it cannot bring all the way there. Okay. So that is nearsightedness. Now, so this is for object that is at distance, and that near point I was talking about, n 25 centimeters. So normal eye should, comfortably be able to focus the light coming from this point. That's the nearest point. So if you bring your, object closer than that, then it becomes blurry, right? So yes, our eyes can see closer than that, but this is universally accepted near point as a normal eye. At, that's what I'm going to be using. So when it is near here, it can still focus on the retina. Okay. So in this case, the object is located at near point, so that's why the object distance is equal to n. And remember, value of n is 25 centimeter. And what is n? Wherever you put the object near to your eyes and you can see, without strain in your eyes, like you don't have to, you know, uh, do much in terms of stretching your eyes. And if you can see that at comfortable distance, that is near point. And for normal eyes, that near point is 25 centimeter. But what happens once it becomes defective? That near point goes farther, remains farther. Okay. So in that case, if you're not using glasses and you need to bring your, let's say, object, let's say if you are trying to read, if you have to bring your paper or phone farther than 25 centimeter, that means now what's happening is your retina, your eye lens is not focusing that on the retina, okay, but behind the retina. So what happens? This eye lens cannot get squeezed enough to make the focal length short enough for this to exactly bring in focus at the retina. Okay. So this is called farsightedness. So what that means is for this eye, the rays of light that's coming from the distance object, let's say far, they can still focus on the retina. Okay. So this is called farsightedness because it cannot see the near. So far-sightedness, far you can see it just fine, but near one you are having difficulty. They call it farsightedness or hyperopia. Okay, so that's the problem. Okay, so what we have to do is we need to use glasses to correct that. So glasses means either converging lens or diverging lens. Converging means convex lens, right? And diverging means concave lens, either one of those. So, we can use that to correct one of those. But what happens is our eyes becomes like, cannot see at 20 and cannot see at large distance. So we need help for both of them. So in that case, you need both kind of lenses. So when you are looking at large distance, usually you are looking at upper part, right? Your eye is wide open. So you are looking from the upper part of the lens, for example, glasses. So correct that vision, they put a kind of lens over there, right? And then when you are looking at distance or near object, what you are doing? You are looking from the lower part, right? And so that's why they have this progressive lens that becomes, like one kind to another kind. So combined lens. And there can be other kind of defects as well, of course. So here I'm just focusing on these two. So that gives us general idea about the defects. So now for fixing, looks like it is a good time if we take break, looks like, otherwise it's going to take a little longer. Okay, so let's take a break, and when we come back we're going to talk about how to correct these visions using glasses or lens. Okay, okay folks, so welcome back. So we're talking about, okay, there are two kinds of defect we will be talking in this class. One is called nearsightedness, another one is farsightedness. And nearsightedness is also called myopia. And how do we, so what's the problem? So for example, in this case, in this image or photograph, you can see this person can see this kid who is closer just fine, but the kids that are farther over there, Like, okay, who are those? Are they my kid or someone else's, right? Wondering. So problem is that the light coming from distance object are, they are not focusing at the retina. So they are focusing earlier. So if we can remember, okay, they are focusing earlier. See, it's coming from far, so focusing earlier than the retina. If we remember that what the problem is, then come up with the solution gonna be easier. So for example, see these light are focusing earlier, so we need to make them go a bit further to the retina. Okay, so how do we do that? So we have a choice of using either converging or diverging lens. So converging lens, if we were to use converging lens or convex lens, they would be focusing even closer, right? So that's what the converging lens does. But we want to move them a bit farther, so that's why we need a diverging lens. That makes sense, okay? So these rays pushes them a little farther so that they exactly fall on the retina. So for that, we need a suitable focal length for this lens. We cannot just put any lens. We need a suitable uh, focal length lens, right? So now, to calculate focal length of that lens, focal length of the lens required to correct this defect, if we can think and remember, how this process, let's say, works, something like this, then it's going to be a lot easier to solve problem. Okay, so let's see what I'm talking here. Okay, so so the power point supposed to be at infinity, but it just moved somewhere closer, right? So there is going to be a power point for a defective lens defective eye that is not equal to infinity anymore. Okay, so it has some value. So that means object distance going to be some value of object distance, right? So now what this lens is doing is, so it is making an image of the object that is far. Okay, so it's making the image of that object at that point. So that means this defective power point, this distance becomes the image distance for this lens. Okay, so this is very important to let's say easily solve this problem if you can remember. So image distance here, this becomes image distance, and since this is virtual image, it's forming in front of this lens on this side and not exactly converging the real rays of light. So real rays of light, they are going down there, right? So this is virtual image distance. This is equal to the power point of that defective eye. Okay, so that's what I'm describing here. The lens forms the image of the distant object at the power point. So that means we know both. So we want this eye to see distant object, means object distance has to be infinity. And now this lens has to make image at the far point of this eye lens or eye. So that means Q has to be negative of that far point. So once we have P and Q figured out, we can figure out the focal length. Okay, we can calculate the focal length of the lens needed. Okay, and that's what I'm writing here for correcting lens. P has to be infinity and Q has to be far point of that defective eye. Now you can calculate F. So using the lens formula, So we are trying to find f, so let's write something like this, 1 over p plus 1 over q. So now what happens? P is infinity. So we are trying to find f, and infinity, let's plug that in, and 1 divided by very large number goes to 0. So this term becomes 0. And then now, this 1 over q, q being negative power point. So 1 over at negative power point. So this becomes 0, means f is now equal to negative power point. So focal length has to be exactly at the power point of that defective eye. Okay, so that's how we can figure out what the focal. But when we have, we go to the doctor, they write power, not the focal length. It is inverse of the focal length. We'll talk about that soon. Okay, but if you have negative power, that means you have to use this diverging lens. So negative sign simply means this focal length is the focal length of diverging lens, okay, or concave lens, which is thinner at the middle and thicker in the side. So if you have negative power, that means you have nearsightedness or short-sightedness or myopia. Okay, so that's the problem you have. And that is the solution. Find a focal length, calculate the focal length. Okay, it's kind of easy. So just keep moving wherever, farthest. Okay, maybe not like this, but put something on the wall and then move away from the wall until it becomes, it starts becoming not so clear. So that's your far point, defective eye for the far point, right? And that's the focal length your lens need. Okay, so that's how we correct it. Now another defect, farsightedness, also called hyperopia. So in this case, we already talked about the problem, right? So light from normal near point cannot focus at the retina, rather it goes farther. So if you want to bring this closer, then you need this converging lens. If you were to use diverging lens, it's going to go even farther, okay? And so you need converging in this case. So that's easy. And near point now has shifted far from the 25 centimeter. So this is the near point of the defective eye. Now we want to correct the vision. So that means, how do we do that? So the image formed by this lens has to be at the near point of the defective eye. So this is the near point of the defective eye. So you put object here, and then image has to be formed here. So that means you can calculate the focal length similarly. Okay. So for correcting lens, object distance, because that's where we want to see it, right? So object distance is going to be at near point. And then image distance, so image has to be formed at the far point, or sorry, near point of the defective eye. Okay, so that's that. And again, this being virtual image, what happens? Maybe I should have made these full and these dashed line. I think I made a little bit mistake here. Yeah, this should have been the dashed one, and this should have been the full line. My bad. Okay, So that's that. So you should be able to calculate the focal length. So for that, again, use the same formula. Okay. So now P is 25 centimeter. So we are writing that in centimeter. Yes, of course, you can convert that in meters as well if you like. 0.25 meters, right? And then minus 1 over whatever that Q is. Okay. That's, let's say, near point of that defective eye. So now this number is known. So defective eye, how far it can see just fine from the, what is the closest distance from where it can see, and that's going to be the nearest point for the defective eyes. So we can figure that out, right? And that's that. So when you go to doctor's office, that's basically that's what they do, right? So they try to determine your points there, but eventually they end up just using different lenses so that you can see it clearly. And that's how they write the prescription. So you can solve for F. And once you have F from both, for both cases, then you can find the refractive power, which is 1 over focal length. Okay. So if you are calculating power, refractive power, you are just calculating 1 over F, so you don't need to invert it, right? So it's just 1 over F. And remember, this power is not like a mechanical power we learn, a rate of doing work, right? That's not what that is, rate of change of energy or rate of doing work. This is just a name given, it's not a real power. It is basically, would have been better in terms of focal length, but looks like, some people in, let's say, a Bayesian industry, they do not want to invert that 1 over F. So they just leave 1 over F and they call it power. Okay. And so for mechanical power, electric power, we know the unit is watt. But here, that's not the case. So unit of focal length in SI unit gonna be meters. So the unit of power gonna be 1 over meter. And that 1 over meter is also called diopters. So basically that's what it's called, diopters. Okay, so then ID. Okay, so that's how we correct the vision. Isn't that wonderful, folks? Okay, so now at this moment, I like to remind you, or let's say, I don't know you've been using this or not, but for example, I have this physics 2 notebook where I have put, what are the things that I put in here? So all the class links from the YouTube, I put that in here. It's not complete. We have only up to class number 16, right? But other than that, the OpenStack book and my note. So my, notes are not totally finalized, but I think, the content wise, I put together all the notes now during this spring break. So that's how I spend my spring break, writing the notes and drawing some of these diagrams. And I haven't finished drawing all the diagrams, so I think probably it's not going to be complete, but in terms of diagram, including diagram, but the content is all there. And I put together all the notes from all the chapters in one note. Okay. And I have posted that on folder on the Canvas notebook LM source or something like that. Yeah, I think that's how I have named it, notebook LM source. Okay. So I put that, all of those together. So now you can easily upload these book chapters in that note, my note, and then you start asking question. And if you have time, you can also link these, let's say, lectures. It takes a little bit time, so it took nearly, I don't know, 8 or 10 minutes for me to, copy and paste. So I went to the that's list, right? Playlist. So our playlist is physics to spring 25 or something like that. So I went there, so it lists the videos, and then I uh, grab the source, shareable source, right? Link to the shareable source, and then brought it here, and then I add source, and then there is this YouTube thingy. So when I do that, it allows me to paste that link over here, okay? But here I already did those, and they are here. So now let's ask a question. Let's see if it can help us to solve problem related to defect in eyes, for example. How to find focal length and power of lens required to correct far sightedness, let's say. Hmm. Oh, spelling is not correct. Okay, so now it tells you, okay, so farsightedness means hyperopia, and now it says near point 25 centimeter, correction using converging lenses, right? So in this case, we are assuming lenses are thin, the lens we use, and we put that very close to the eye, okay? And you use this formula, and P gonna be the, near point, and then Q is the image distance, which is the negative of farsighted person's near point. So I don't know how good you can see it here. Where? So it gives you that, and then one near point of the hyperopic eyes. So all those things are written right here, and even gives you an example based on source 19, it said. So that is from my note. So I have done some problems over there. So basically it's just using that here, okay? And then it also summarizes at the end. Very good tutor if you know how to use it properly to learn, okay? Okay, so new update is I have now posted the notes fully. So you have chapters from the book and my notes. Okay, with that, now I have a question for you. You have 2 minutes. 30 more seconds. Five more seconds. 5, 4, 3, 2, 1, and it stops. Okay. Let's see what we got. So mostly A and B. Let's see what we have. A concave lens reduces the focal length of the eye lens. Okay, focal length of the eye lens. If it does, then it would even converge even closer, right, to the lens rather than pushing it farther towards the retina. So that's why this is not correct. And we know the focal length of the eye cannot be changed using the lenses. That is changed by the muscle, okay? So that's why that is not correct. A concave lens forms image at the far point of the defective eye, okay, allowing it to see the image. So yeah, the B is the best choice here. So it's not behind, it's the in front. Before retina, it just says in front of the retina right there, right? Not behind. The power of the corrective lens for myopia is always positive. It's not, it's always negative because we use diverging lens or concave lens and it has negative focal length. So that's why it is not correct. So only B is the correct choice. So now here is a question, okay? Another question. Let's do 30 more seconds. And now 5 more seconds. 5, 4, 3, 2, 1, and it stops. Okay, let's see what we got. So we got all of them. So mostly B. It's in B. So here, my near point is just fine. 20 centimeter, even less than 25 centimeter, right? The problem when it cannot, like see 25 centimeter or less, but here it can see that, I mean, yes. So even if it cannot see like within 25 centimeter, then that's a problem. But here it's seeing 20 centimeter means that is not a problem. My far point, normal should be infinity. But I cannot see, I can only see up to half meter. So what that means, I have problem here with my PowerPoint. Okay, so that means whatever lens I use, it has to make image at that point, and that image is going to be virtual no matter what glasses we use. And we know the diverging one or the concave, it always makes virtual image, but converging can make virtual image. But in this case, what happens? The image is going to be on the same side, making it, like it also has to make virtual image. Real image has to be on the side of the eye, but our PowerPoint is not on the side of the eye from the lens, right? So it's going to be virtual. So it has to be at PowerPoint and it has to be virtual. Okay, that was not on the choice. So it looks like B is correct answer in this case. Okay. Now, let's say I want to correct that vision. Means once I have this information and this is how it works, that means now I can calculate the focal length, okay, and power. So for this case, oh, now I cannot write. Okay, so now P, we want to see the object sitting at infinity, okay? PowerPoint, we want to correct the PowerPoint. So that's that. And now image has to be at that point. So negative 50 centimeter, okay? And now the question is, what is focal point? And focal point of the lens. So using this formula, 1 over infinity plus, actually it changes to negative sign. So let's write negative because Q is negative, 1 over 50. And this is in centimeters. So this becomes 0, means F is negative 1 over 50. Oh, not 1 over anymore. It's just 50 centimeters. So that's the focal length. Now power is 1 over focal length, which is same as whatever we had. So negative 1 over 50 centimeter. But for the power, to get it in diopters, it has to be in meters. So we need to convert this into meter. Means it is negative 2 diopters. So that's how we do that. So now here is another problem. Harry cannot clearly see objects closer than 1 meter. What kind of problem Harry has, and what refractive power his glasses should be. What is the problem here? A, nearsightedness. B, far-sightedness. Okay, I'm just giving you two choices and opening the poll. So go ahead and poll on it. Thirty more seconds. And 5 more seconds. 5, 4, 3, 2, 1, and it stops. Okay, let's see what we got. It's competing. We even got C. So there is a bit more for C. Okay. So Harry cannot see object closer than 1 meter. So problem with near sight. So far sight is fine. Okay. And that's how it is named. So farsightedness, B is correct answer in this case. Okay. Okay. So now how do we solve this problem? So we need focal length so that we can find power, right? So that's what it is asking. And see, the power is uppercase P, okay? And for object distance, I'm writing lowercase p. And for image distance, what's q? So we need this. So what should be P in this case? Object distance, okay? Where should we put the, what should be the object distance for this one here? So A at near point, B at infinity, and C between n and infinity, and D is 1 meter. Let's see what should be value for now. Okay. So I'm now going to open poll on this question. And for this, you have just 30 seconds. Okay. Five more seconds. 5, 4, 3, 2, 1, and it stops. Let's see what we got. Oh, we got all of them. Tough question. There is a bit more for A and C. So cannot see closer than 1 meter. So that means we need to correct this vision so that it can see at the near point for the normal eye. So this is the near point of the defective eye. So this is near point of defective eye. It cannot see near than this means that is the nearest point it can see, right? So near point of the defective eye. And what we want to see the object at that near point at 25 centimeter. Okay, so that's why the P has to be N or 25 centimeter. Okay, now we want the image of this to be formed at this near point of the defective eye, so Q has to be negative 1.0 meter. And this is centimeter, this is meter. Not a good idea. We have to convert both of them. Since we are finding power, and for power we need in meters, so it's a good idea to convert this into meters. Okay. So now 1 over F is 1 over P plus 1 over Q. So 1 over 0.25 minus 1 over 1. So the positive becomes negative because Q is negative here. So this is just 1, right? So now, I think in this case it's easier. 1 divided by quarter is 4. And then this is 1. So that is that. So this means it is 3. So 1 over 4 is 3. Sorry, 1 over f is 3. What am I saying? So 1 over f is 3, means power is 1 over f, means 3. So looks like we are getting positive. And the unit going to be D because we use these in meters. Okay. So this is 1 over meter because focal length has to be in meter. This is 1 over f we're talking about. So this has to be 1 over meter or per meter. So looks like for this we need to use converging lens, and that makes sense, right? Okay, so that's that. So now I have another question for you. It basically tries to summarize things we learned regarding defective vision. Oh, what happened to this cage? Okay, so I need to make a sketch here, okay? So let's suppose this is eyeball and ray of light, distant object means that. Okay, now that's the sketch. My bad. And 30 more seconds. 5 more seconds. 5, 4, 3, 2, 1, and it stops. Okay, let's see what we got. We got all of them. So it is not focusing on retina, means that's a defect. So it cannot see distant object. Problem, distance for the distant object. Okay, so that means near point, no problem. So that means it is nearsightedness, and nearsightedness is also known as short-sightedness. Okay. So it has short-sightedness, so that's why A and B are not correct. Problem with long or distant object means nearsightedness. See, sightedness, it can see it just fine. That's what that name means. It's kind of opposite, so that could be confusing. Okay, now see, it's converging closer. So if we want that to go all the way, we need the diverging lens here. Sure, diverging. Okay, so it looks like D is correct answer in this case. Turned out to be tough question, huh? Okay, so we talked about, let's say how the microscope and telescope works already. It uses two images. So here, when we have two lenses combined, how it works, basically lens one first makes image. Okay, so here this lens one is making this image, and this image could be anywhere depending on its focal length, right? And then now you can figure out where the image is going to be by using this formula, if you know is where the object is and what the focal length is, right? So once you figure out its image distance, that image distance now becomes the, that you can figure out the object distance for this, okay? So lens 2 could be here or could be here, behind that. So that situation we saw when we looked at the microscope, we had something like this lenses, right? So we can have also this diverging lens over there. So when we have that, what do? You use lens formula once, and now you use the lens formula one more time. So in this case, this is going to be the object distance, and this P2 has to be written as a negative, okay? Number here, whatever that is. And that, if you know what's the distance between these lenses and what is the image distance, then you should be able to figure out P2, okay? And then now you use this formula to figure out Q2 or focal length if you know Q2. So that's how you use that in two steps if you need to do that, right? So P2 becomes this S minus Q, where S is the separation distance between two lenses, okay? So that's how it works. I'm just giving you overview. And camera I was talking about. So this is how the camera works. So it has the detector here, and there is one lens. And depending on what kind of camera you are using, you may also slightly change the focal length of the lens, right? Adjustable focal length lenses. It goes from certain value to another value, and it's written on the lens, okay? Or it could be fixed focal length. So I think I may have a lens somewhere here. Or maybe not. So it's already 50, so I'll let you go before I find my lens. One lens is mounted in my camera that has a fixed focal length. So anyway, so that's how this works. So it makes inverted image. So it makes inverted image in our camera software, basically, inverts it back. So back in the days when we had a film used to have this negative image, what we called, okay? And that's what this inverted image means, because this convex lens makes inverted image, okay? So I'll see you folks next class.